Hello guys, my name is Zoe and my YouTube channel is DRG Bros, and welcome back to Eigenvectors 2. So topic 1 is going to be our review. So for notation, capital letters represent matrices. For example, A equals 2, 1, 5, 3. And so lowercase letters mean column vectors. So for example, B equals 1/2, or 1/2. So all linear systems can be written as matrix equations with this notation. So for example, if we have the integral, linear system 2x1 plus 1x squared equals 1, and then 5x1 plus 3x2 equals 2. And so if we have 2153, and then let's say we have x, so x1, x2 equals b, we get something like this. A x equals b, giving us this formula: A x equals b. And so what we can do is we could say that we can multiply each side by the inverse. So we can add a -1 and then a -1. And so this gives us the inverse matrix of x equals a -1 b. And so this equals x equals a -1 b. And then there's some operations on matrices. So we can have a -1 equals 3, the inverse a equals 3, -1, -5, 2. Then there's the transpose, which is A transpose equals 2, 5, 1, 3. And then there's the conjugates, which is 2, 3 plus I, 2 minus I, -I. And so there are also 2 more, which are theorems, which is AB -1 equals B -1, A inverse. That's how you switch them around. And there's also the trace. And so the trace is the trace of AB, A times B, equals the trace of BA. Okay? And so moving on to topic 2. Important matrix names. So if we have symmetric, we have something like this: 1, 5, 8, 5, 2, 6, 8, 6, 3. And so if we transpose this, then we get the exact same thing, because 1, 5, 8 5, 2, 6, 5, 2, 6, 8, 6, 3, 8, 6, 3. And we have a Hermitian. Then we have something like this. 1, I, 2 plus I, negative I, 2, 4 plus I, 2 plus I, 4 minus I, and then 3. And so we get the exact same thing. We get 1 negative I, 2 plus I, 4 minus I, 3, 4 plus I, 2 I, 2 plus I. And then we have the diagonal matrix. And so this is just that all of the off diagonal elements are 0. So this is diagonal. We have an elementary matrix now. And so this is if we have, for example, if we have an identity matrix, 0, 0, 0, 1, 0, 0, 0, 1. This is if we get the elementary matrix is the matrix that we get by doing one row operation off the identity matrix. So R1 plus R2 into R2 gives us 1, 0, 0, 2, 1, 0, 0, 0, 0, 1. A permutation matrix is where 1 appears only one time in a row or column. So this is basically an identity matrix. So if we have A, B, C. Oh, sorry. We have here, let's say 0, 1, 0, 0, 0, 1, 1, 0, 0. This is a permutation. So it's basically, it's the same value. It's just taking A, B, C and turning it into B, A, C. All you're doing is just scrambling up the numbers. And so a matrix, an orthogonal matrix, is where the transpose of O equals O is the inverse of O. And so O equals square root of 3 over 2, 1/2, negative 1/2, square root of 3 over 2. So the transpose is transpose of O equals or 3 over 2. And so the key idea here is that O times OT equals O times O, or inverse O, which equals the identity matrix. So we can move on now to our final one. A matrix is called unitary if conjugate of u is equal to u. So for example, here we have u equals 1 over the square root of 2, 1 over the square root of 2i, 1 over the square root of 2, 1 over the square, or negative 1 over the square root of 2i. This gives us one over the square root of 2. Also box that. Negative 1 over the square root of 2i. 1 over the square root of 2. Negative 1 over the square root of 2i. So moving on to our final topic. If we have a to the x equals lambda x. And so a x minus lambda x equals 0. And so a minus lambda I x equals 0. And so we need to note that x is essentially equal to 0, 0, which is called the trivial solution. And so x can be non-trivial if and only if the determinant of a minus lambda I equals 0. Thank you guys for watching. I hope you enjoyed, and I'll see you next time. Bye.